everyone, Katrina here, and today we're going to go through a bunch of Cartesian vector examples. Please subscribe for more videos like these and watch to the end to see all the examples unfold. Okay, let's dive in. In my previous video, I gave a full tutorial introduction on Cartesian vectors. For this video, I'm going to take you through examples so you can see that theory in action. So make sure to see the previous video so you can get that background that you need. So we're going to dive right in with some pretty exciting examples. So first of all, let's consider some vector A that equals to 5 and negative 6. So knowing what we know about vectors, we know that first of all that this is two-dimensional, and this is a Cartesian vector, is also an ordered pair. And what else do we know about it? So an ordered pair means that this 5 kind of represents our x, and this negative 6 represents our y value. And this is also considered to be an algebraic form, which is also called ordered pair notation. So the reason why I'm just showing this right now is because sometimes it's important that as soon as you see a vector that you can classify what type of vector it is, because once you know what it is, you're able to extract properties from it. Just like how we know that this 5 over here represents our x component and this 6 over here represents our y component. So for this question, I want you to rewrite it in terms of I and j. So remember that let's see, what does I equal? So I is our unit vector in our x direction. So that means I is 1, 0. And j is our unit vector in our y direction. So that means that it's 0, 1. And what do we know? So if we have this vector over here, we can rewrite it. So let's say we have vector A. We can rewrite this. And let's say A is composed of some component A and B. It can be rewritten as A times I plus B times J. So that's kind of how we go from this ordered pair algebraic notation to our unit vector. I call our unit vector notation. So let's go ahead and do that. So now that we have this information, this is actually a very easy problem. So our A or x is going to be 5. We multiply that by I, and then plus, in this case, we have negative 6, and then j. So we can simplify that such that we have 5i minus 6j, and this equals to our vector A. And this helps us understand the components. That means if we were to start at the origin, we would go 5 units. Let's draw that out together, actually. We would go 5 units to the right, so we go 1, 2, 3, 4, 5, and then we want to go 6 units down. So we're going to go, so we'll do the 6 in green, so 1, 2, 3, 4, 5, 6, and then we start our origin, and then tail at the origin, and head at this final point over there, and then this here is our vector A. So that's pretty neat how we can see the correlation between kind of starting at a point on a Cartesian plane and then using each component to help us gradually step by step get to our final vector that we want. So I always encourage you, especially in 2 dimensions, to kind of do that comparison back and forth between algebraic form as well as the kind of the Cartesian, the drawing, the representation on the graph, because it's really good to help you understand that relationship between the graph and the algebra so that you can visualize that vector a little bit better. Okay, so that is one example of how do we rewrite something. Let's do another example of trying to find a vector. So say we have 2 points. We have point A, which is negative 2 and 3, and then we have another point, which is B, which is 4 and negative 5. We want to find vector BA. So like I mentioned in my previous video, this first letter here, this represents our tail, and the second one represents our head. So that means that we have some point I don't know exactly how this vector looks right now, but if we have some arrow, we know that this tail is our B and our head over here is A. Well, how do you find this? In order to do this, if you want to find vector BA, which is this one over here, we have to do the head. We want head minus tail. So that means we're going to do A, vector A, or sorry, not vector A, point A minus point B. And we have A and B right there. So let's just do that simple subtraction. So that means we're going to note that we're doing element by element. So we subtract the x's together as like one pair, and then secondly, we would subtract the y's together. So if we write that out over here, we would have, in terms of our x portion, we'd have -2. And then that's our a minus b minus 4. So that's our first point. And then our second point is going to be our 3 minus our 5. Oops, sorry, minus -5. So minus -5. So we have to be wary of the double negatives here. So that means that we end up with 2 minus 4, which equals to -6. And then 3 minus -5, well, this double negative turns into a positive, so which is 3 plus 5, which will give us 8. So that means we have just found vector BA. Okay, so that's another great skill. Given 2 points, how can you find the vector? Awesome. So let's do another example. Another skill put into action. So say we have some vector A equals to 7 and -6. We want to determine what is the magnitude, sorry, I can't spell and talk at the same time, determine the magnitude of A. So it's kind of like the quote-unquote absolute value. And we want to find this in the exact form. So that means if we get some square root, which we probably will, we want to keep it in that square root. So recall the formula. So the formula for absolute value, so say we have some vector x, y, the absolute value of this vector is going to equal to the first component squared plus the second component squared, and we take the square root of that. So you might want to think of Pythagorean's theorem with this as well, because think about it, you have your x component and you have your y component, and we want to find that hypotenuse. So if we were to take this y over here and shift it all the way over to this side, we have this xy triangle, and we're looking for, you can think of that as h, or hypotenuse. Okay, so now that we have the formula, this becomes pretty easy. We just have to fill it all in. I really recommend when you're doing examples is to write out theory first, write out the formula that you're going to use, and then plug it into your formula. The numbers should always come last, because that helps you make the least amount of mistakes possible, because you have it all set up, and then you're just going to plug and chug the numbers in at the end. So absolute value of A, our magnitude, equals to the square root of 7 squared plus -6 squared, and that will equal to 42 plus 36, which is equal to the root of 85. So that means that we write our therefore statement. So therefore, magnitude of A is root 85, and we're going to keep it in the square root because that is the exact form. Okay, are we ready for one more? Let's try one more together. So this, we need to think of scalar multiples. So in this case, we're going to say that A equals to 3, -5, and we have another vector B, and this vector equals to -4 and 7. So we want to evaluate what is A minus 2B. So the first thing that we have to note is that we have this 2 over here. And what is this 2? This is a scalar multiple. So that means that a scalar, remember, has a magnitude but no direction, right? So when we have a scalar multiple, that just means you multiply this number to all the components of your vector. So as a first step, let's just create that new vector 2b. So we'll write it all out in a line just so we don't lose everything. So we've got 3, -5, minus 2, -4, 7. And like I said, we want to multiply this 2 into both our components. You can think about it as a distributive property. So let's try that. Oops, let's go for the thinner pen over here. So we've got 3, -5, minus, and we distribute this, so we get -8 and 14. And now what we do, since we have the subtraction, we're going to do element by element. So that means that we're going to subtract the x components with each other, and then we're going to subtract the y components. So that gives us, let's break that up. We have 3 minus -8 as our x component. And then as our y component, we have -5 minus 14. So again, just to clear things up, this is our x, this is our y. So if we do that arithmetic there, what do we get? We get 8 minus turns into a plus, so 3 plus 8 gives us 11, and then -5 minus 14 will give us a -19. And remember, this equals to our vector A minus 2 times vector B. So that's pretty neat. So whenever we do this addition or multiplication, make sure that you're doing it component by component. So do your x's separate from your y's. And whenever you have this number in front, recognize it as a scalar multiple and think of the distributive property. So you're just going to take that number and distribute it to both of the components of your vector. Make note that this 2 over here, it only changes the size. So it changes the size of the vector, but it does not change the direction. So since we're multiplying by 2, that means we're stretching this vector by a factor of 2. So given that it's -4, 7, I would think the vector would look like that. And then by multiplying it by 2, we're now going to have a vector, oops, oh my goodness, I can't draw a straight line. Imagine that's a straight line, so it's twice the size, but still pointing in the same direction. And that's what the scalar multiple is doing in that case. So I hope this video was helpful. It put to action some of the introduction to vector principles and just kind of taught you how to do some manipulations to Cartesian vectors. If there's other specific examples that you'd like to see, please comment below. I will be creating more vector videos, so definitely stay tuned. Please subscribe if you enjoyed this video, and I look forward to seeing you next time.